Hi, this is the lab number 9, Power for One Sample T-Tests. All right, here we're going to see how to manipulate, some numbers when we perform an hypothesis test, and we're going to focus here on the power of a test. The power is only the probability of not committing a type 2 error. So let's read this first. Errors in hypothesis testing. Anytime a decision is made, there is a chance of making the wrong one. Always, it is inevitable that we can have mistakes. I mean, the probability of making mistakes is there. Two types of error exist. The first one is better if we see this table. Failing to reject the null hypothesis when it should be rejected is a type 2 error. When you don't reject the null hypothesis, but the null hypothesis is false, is a type 2 error. The other one is when you reject the null hypothesis, but the null hypothesis is true. That is a type 1 error. So type 1, type 2 error. The notation that we have for the type 1 error is actually the level of significance, alpha. That alpha is the probability of committing a type 1 error. The type 2 error can happen approximately beta. This is the Greek letter beta percent of the time. Beta is dependent upon the sample size among other factors. It is usually set to 20%. So here we're going to see how if we manipulate some numbers, the beta, the 1 minus beta is going to change. Power of a test. The probability of not committing a type 2 error is the power of hypothesis tests. If beta is the probability of committing a type 2 error, what is the probability of not committing that? 1 minus that. Power gives the probability of correctly rejecting H0 when in fact H0 should be rejected, being able to detect a difference if one exists. The higher the power, the better. Target value is 80%. In practice, it is ideal for studies to have high power while using a relatively small significance level. But to be honest, we don't cover that here in this course, but you can not only set up the alpha level as minimum as you want, and the same for the beta level. That is impossible. When you are manipulating the alpha and other factors, the beta is going to be changing, right? It's going to be increasing. We're going to see some of that here. All right, 4 factors will increase the power of a test. Alpha, the sample size, increase the sample size, decrease standard deviation, increase distance between null and hypothesized values of the mean. This is H null minus H1. Exploring factors that impact power. There are 4 factors that impact power. In the next exercises, you're going to alter the values of each of the factors to see how the power is impacted. For each test, reset to baseline and only change the one variable indicated. Open a blank Minitab worksheet. All right, the baseline values are this one: alpha 0.05, sigma 1.18, difference 0.80, n equal to 10. Null hypothesis greater than. So let's do this in Minitab. On the drop-down menu, select stat, power and sample size, one sample t. Sample size 10, differences 0.80, Power values, leave it in blank. Standard deviation, 1.18. In options, alternative hypothesis, greater than, significance level, that is alpha, 0.05. Okay. Okay. And there you have. You see the results. The power is 0.631. What is the power? So type here in the activity 0.631. There you have. Now from here you will have to be changing some of the components. For example, first change the sample size, record the power each time. I mean, do we have to do this? I'm going to do only first. I'm going to do this only for the 8. So repeat the process. Stat, power and sample size, 1 sample t. Now instead of 10, change this to 8. And then OK. The power now is 0.534. And so on. That okay? So to save time, please, you will have to complete this. You will have to complete this part. Do the same for 12, 14, and 16, and you will have to record the corresponding number that you see here. This one here, power. This one. All right. Now here, once you are done with this table, you have to reset to the baseline. To reset to the baseline, remember that n is equal to 10. But now we're going to be changing the difference. Again, I'm going to do only one example for this one. So again, stat, power and sample size, 1 sample t. Sample size, remember the baseline is 10. But now we're going to change the difference to 0.5. 0.5. Okay. The rest is the same. The power is 0.343. And you repeat the process with 0.9 and 1.12. Now here again, reset to baseline. The baseline is, remember what, is difference 0.80, so reset to 0.80. But now we're going to be changing the standard deviation. Power and sample size, 1 sample t. Go to the baseline, 0.80. But now we're going to be changing the standard deviation. The standard deviation, the baseline is 1.18. Change it to 0.8. And then OK. The power, notice how the power was increased a lot, 0.89. 0.89 here. The power here, this one, 0.897. Well, 0.898. There you have. And you repeat the process with 1.1 and 1.5. Next, reset to baseline. So again, go to stat, power and sample size, 1 sample t. The difference is 0.8. The baseline is sample size 10. 0.8. The standard deviation was what? 1.18, right? Yeah, 1.18. But now we're going to be changing the level of significance, the alpha. Here we have to do it for 0.01. 0.01, and let's see what's happening. Okay. Notice how the power changed to decreased to 0.30. Decreased a lot. 0.30, 0.31 actually. And you will have to repeat the process with 0.07 and 0.12. That okay? All right. Changing the alternative hypothesis, reset to baseline, and graph the power curves for the other two alternative hypotheses. All right, so I think this refers to we have to now change the repeat the process with the point. Yeah, I mean now you will have to change this to for this one you will have to change to 0.8. So go to the baseline. The baseline is again 0.05. Sample size 10, difference 0.8, the baseline. I'm using the baseline. Power values, leave it like that, 1.18. The options, the baseline for alpha, for a significant, alpha is the significant level, 0.05. But now, here in the alternative, change it to less than 0.05. Okay. Okay. And see, you will have to register the power, 0.001343. That's all that you will have to do for this part. All right, you do the process for different from 0.8. Now, the other part of the activity, objective. This exercise refers to the article Statistics and the Virginia Blood Test Statute, written in 1970. 1970. Back in 1970, driving under the influence was presumed when the blood alcohol level was 0.15% or more of weight. On page 353, table 1, the blood alcohol level readings are provided for several defendants who are identified by their initials. GMB is the first defendant in table 1. I know this is referring to a data set, but actually we don't need it because all the information is going to be provided here. So don't worry about that. GMB is the first defendant in table 1 with blood alcohol levels of 0.20 and 0.18. Test hypothesis mu equal to 0.15 and mu greater than 0.15. So in this case, we will have to test the hypothesis as I have showed in the corresponding video for the module number 11. But fortunately here, we're going to see one way to do it faster, okay? Without doing all the computations. So enter the blood alcohol readings for GMB into column C1 of a Minitab worksheet, 1 per cell. Do you think that GMB with a mean blood alcohol level reading of 0.19 is guilty of DUI beyond a reasonable... DUI, remember, means driving under the influence beyond a reasonable doubt? All right, so one sample T. Let's use hypothesis testing to arrive at a decision. In C1, enter the values 0.20 and 0.18. So We're going to be doing this for 2 values only, but if we have more than 2 values, we can perform a test only by putting all the values in one column. In this case, the column C1. On the drop down menu, select stat, basic stat, 1 sample T. Here, 1 or more samples, each in a column, leave it like that. The values are from C1, so notice I already have them here. C1, no, not twice, only once. Select column data C1, select the checkbox for perform hypothesis test. I mean, this box for you is not going to be checked, so click on that box. There you have. Hypothesize the hypothetical mean is 0.15, so type 0.15. I already have it here. Select option box. Alternative hypothesis mean greater than hypothesized mean. Notice I already have it here. Mean greater than, and okay. And with that, you're going to obtain the result for the p-value. That is what we need to make a decision, all right, as to reject or not the null hypothesis. So questions. Based on the hypothesis test p-value, what is your decision? Reject or fail? Since the p-value is given here, you have it 0.078 is not less than 0.05, then we do not reject. Fail to reject. I'm going to highlight this. Fail to reject H-null. Which error are you at risk of making? Actually, the 2 errors, but when we're talking about this, the alpha is type 1 error. There you have. Now, so what is the meaning for this? We are not rejecting the hypothesis that mu is equal to 0.15. So, I mean, based on only this sample from this person, we don't have, based on this hypothesis test, we don't have evidence to say that this person was driving under the influence of high blood alcohol level, because we are not rejecting 0.15. That okay? But let's see what's happening when we manipulate the things a little. Pause power. Are you surprised that GMB is not guilty at the 0.5 level of significance while we obtain the power 1? Let's do a post hoc power analysis and determine the power of convicting someone that is driving 0.05 units above the legal blood alcohol levels of 0.15 units. So now from here, we're going to be manipulating the values. On the drop-down menu, select stat, power, and sample size. 1 sample T. Sample sizes is 2. Differences, 0.04. Power values, leave it in blank. Standard deviation, 0.014. Options, alternate hypothesis greater than, level of significance 0.05, okay, and then okay. Notice, in this case, we got the power 0.47. 0.47. We're trying to get the value equal to 0.80. So we need to increase something. I mean, manipulate something, either the sample size, standard deviation, the level of significance. maybe the difference between the null and the alternative hypothesis. So let's see what's happening, right? The next we're going to be manipulating this, but here for the first part, we got 0.47. Now, sample size. See, but one problem with this is because our sample is very small. I mean, only 2. It says since 2 is not enough, how many blood samples will be needed to have 80% power to detect someone that is driving with 0.04 units over the legal blood alcohol level, 0.15, at the 0.05 level of significance. So now again, go to the stat power and sample, one sample T. Leave in blank the box for sample sizes. Differences 0.04, power values right 0.80 because this is the power size we want. Standard deviation the same, the options the same, and then okay. What is the sample size that we need? It's this one, 0.3. You see? Notice Minitab gives you the target power that is 0.8, but the actual power that we get with the sample size equal to 3 is 0.91. So we only need 3, right? So it's amazing. 3. How many samples? Here, right, 3. Changing the sample number would increase the power, but the state cannot afford to do more samples, so something else must change. Now, what about if we change the difference? With only 2 samples of an 80% power, what difference in blood alcohol level from the legal limit of mu equal to 0.15 is needed? Now, repeat the process. Go to stat. So you see, it's only we're going to be changing the values. One sample T. Sample sizes is 2. Differences, leave in blank. Power value 0.80. Standard deviation 0.014. And greater than and significant level 0.05. So the needed difference is 0.08. 0.081. It is one here. You see it? 0.081. Now, changing the limit. The current legal limit in the US is changed from 0.15 to 0.08 watt concentration level for anyone 21 or over. But any detectable amount of alcohol is illegal for anyone under 21. Determine the power of convicting someone that is driving with a 0.19 blood alcohol level here and now, using 2 blood samples and the 0.05 level of significance. So now we're going to be changing the limit. Instead of 0.15, now it's going to be 0.08. On the drop down menu, select, so go repeat the same, start, 1 sample T. Power and sample size, 1 sample T. Sample size 2. Differences, now the difference is going to be 0.11. How do we get that? From 0.19 and 0.08. The 0.19 is from this guy that it was BLM, I think, right? Or I don't know. So it's 0.11. Power value, leave it in blank. I mean, we're looking for the power, 0.014. Greater than this, the rest is the same. So okay, and here you have the power is 0.917. 0.917. Is this one? You see? 0.917. Well, 0.918 actually, right? Now, finally, hypothesis test 2. Let's use hypothesis test again, the new limit to determine if the original defendant is guilty or not. test the hypothesis again against the new blood alcohol law. So everything's going to be the same, but now we're going to be changing the hypothetical value, or the hypothesized value, and the alternative. All right, so go to the beginning. This here, do we have to repeat these steps, these instructions? Let's use hypothesis testing. Go to stat, basic stat. We're going to perform one sample team. The values from C1. Now, the hypothetical or hypothesized mean is 0.08. Options, the alternative is mean greater, so the same. Confidence level, leave it like that. C1, I think everything is correct. And then OK. Now, what is the p-value? The p-value you see now is 0.029. The p-value p-value is equal to 0.029, and since the p-value is less than alpha 0.05, we reject the null hypothesis and we reject H null. So notice with the new level, the person would be guilty. P-value is 0.029. Which error are you risk of making? Actually, the two, right? I don't know why this question is asked. Always you are at risk of making the two errors, but I think in this case, because we're focusing on we are not focusing on the power, so it's type 1 only. I mean, I can select only type 1. But always, I mean, always, when you're performing an hypothesis test, you cannot avoid the risks of making the two errors. It's impossible. So that's all right. All right, guys, that's all by now. See you in the next lab activity.